In this video, I want to have a look at binomial expansions and how they relate to Pascal's triangle. So a binomial just means something with two terms. So we've got our two terms in our bracket, and we're going to expand this bracket out. So this first one, you should know fairly well how to expand that. It's a perfect square. So we just end up with 1 plus 2x plus x squared. If we had a higher power, so if we had 1 plus x cubed, first we'd expand that to be 1 plus x squared, 1 plus x, and then we could expand this bit like we did up the top. So we'd have 1 plus 2x plus x squared, 1 plus x, and then we could go through and expand out that. So we'd have multiplying everything by the 1, we'd have 1 plus x, multiplying everything in the second bracket by the 2x, we'd have 2x plus 2x squared, and then multiplying everything by the x squared, we'd have x squared plus x cubed. And then we'd have to collect all those terms. So we'd have 1 plus 3x plus 3x squared plus x cubed. Now for a cubed, that's still okay. It's a bit more work, but it's not too bad. But you can imagine as our powers get higher and higher, this is going to be quite a long process to go through and expand things one at a time and then collect like terms and keep going. So what we want is a shortcut. We want to find a pattern in these expansions so that we can apply that when we have, say, to the power of 7, for example. So if we have a look at a whole pile of these expansions, and we could have kept going, but I've stopped at 7. So we started with a power of 0, which would just give us 1. The power of 1 would just give us our 1 plus x. We have these two, which are the ones we just expanded, but you can go all the way up, and we've got a few so we can start seeing patterns. So the first thing that I want to have a look at is the powers of x. Now we know that if we've just got an x, we could write that as x to the power of 1. So that's all of these ones down here. And if we've just got a 1, we could also write that as 1x to the power of 0. So that's all of these ones could have an x to the power of 0 on them. So if I write those all in, so I've put all my x to the power of 0s in there, and I've put all my powers in red so we can see the patterns. So if you have a look along each line, you can see that each term has an x with a power that increases by 1 each time. So if we look at this bottom one, we've got x to the 0, x to the 1, x to the 2, all the way up to x to the power of 7. So that's one pattern that we need to notice. The other one is to do with coefficients of x. This time I've highlighted all of my coefficients in red. Now at first glance, these numbers don't appear to be too special except for the fact that they're always symmetric. So for example, if we look at this bottom line, we've got 1, 7, 21, 35, and then we go back down. So we've got 35, 21, 7, 1. In the 6s, 1, 6, 15, 20, and then back down 15, 6, 1. So that symmetry is really important. But the other thing is what's special about those numbers. So I'm going to pull these numbers out, just the coefficients, and I'm going to arrange them into something called Pascal's triangle. So over here, I've pulled out my coefficients. So in that top row, I've just got a 1. In the second row, I've got 1, 1, then I've got 1, 2, 1, and so on. So pulling those coefficients out and arranging them in this triangle. Now, Pascal's triangle has a huge number of really cool properties, but for now, I just want to have a look at how it's built. So if we want to build a row in Pascal's triangle, we always start with 1, 1, 1, and 1s go all the way down the edge. But to fill in the middle of the triangle, our number is going to be the sum of the two numbers above it. So to get this 2, we had to do our 1 plus 1. To get the 3, we'd do the 1 plus 2. To get, for example, the 15, we're doing the 10 plus 5. So adding the two numbers above it to get that one. And we could continue that triangle on forever. Combining those two things, we can use Pascal's triangle to find the coefficients. And then after each of them, we just put an x with the power increasing. So we'd have 1x to the power of 0, 7x to the power of 1, 21x to the power of 2, and so on along there. But it's still not a huge shortcut if every time we want to do this, we have to write out Pascal's triangle. So we've got something else as well. The Pascal's triangle and the numbers in there can actually all be tied back to the work that we did on combinations. So if we're trying to get the numbers in this 6th row of Pascal's triangle, for example, then we're going to have 6C0, which would give us our 1, 6C1 would give us 6, 6C2 would give us our 15, and those are going to give us our numbers for our triangle if we go the whole way through. So if we know, for example, that we want the 7th row, then we can just go through and figure out those combinations to get these numbers, rather than building the whole Pascal's triangle. One other thing I want to make really clear is some notation. So we write often NCR like this, but you can also write it in this form here. So that is combination notation with the N up the top and the R down the bottom. And those two things mean exactly the same. So for example, this term here, that's 7C6, I could also write as 7,6 in brackets. So that's notation you might see in your textbook or just anywhere else in exams, things like that. So our first example asks us to expand 1 plus x to the power of 5. So looking at my fifth row, we've got 1, 5, 10, 10, 5, 1 as our coefficients. And we know that we're going to increase the powers of x each time. So expanding that, I'm going to have 1x to the power of 0 plus, what was the next one? Where are we? Here. So we'd have 5x to the power of 1 plus 10x squared plus 10x cubed plus 5x to the power of 4 plus x to the power of 5, or 1x to the power of 5. And then I can simplify those down a little bit. This is just going to be 1 plus 5x plus 10x squared plus 10x cubed plus 5x to the power of 4, and then just plus x to the power of 5. We can also extend these expansions to terms where the first term in our binomial isn't 1. So in this one we had a 1 plus x, here we've got an a plus b. So that b is going to work the same way that x did, in that it's going to start with a b to the power of 0 and it's going to increase all the way up to b to the power of 7. But this a is going to go the other way. So it's going to start off with a power of 7 and it's going to decrease each time. But the coefficients work exactly the same. So if we have a look at this one, we've got this bottom row here. So expanding this out, I'm going to start with 1 as my first coefficient. I'm going to have a to the power of 7 and b to the power of 0. Then I'm going to add, my next number is 7, a to the power of 6, so decreasing that power, b to the power of 1, increasing the powers of b, plus 21 a to the power of 5 b squared, plus 35 a to the power of 4 b cubed, plus another 35 a to the power of 3 b to the power of 4, plus, where are we up to, another 21, so 21 a squared b to the power of 5, plus 7 a to the power of 1 b to the power of 6, plus the last one, 1 a to the power of 0 b to the power of 7. So we could simplify down the first and last terms there. This one I could just write a to the power of 7. And this last one I could just write b to the power of 7. But same sort of process, but one pronumeral, its power is increasing while the other one decreases. So to write all that in general terms and using combination notation rather than Pascal's triangle, we can say that if we have 1 plus x to the power of n, to expand that we'd have nc0, so that's going to give us our 1, our first term in that Pascal's triangle row. Then we're going to have nc1 x plus nc2 x squared plus, and then when we get to a specific term, it'd be ncr x to the power of r, all the way up until we get to that power of n term. If we want to write it in summation notation, we could write it as the sum from r equals 0 to n of ncr x to the power of r. To write that even more generally, if we look at something similar to our second example, we've got a plus b to the power of n, then we're still going to have those same coefficients of nco, nc1, nc2, but our a is to the power of n, then we've got a to the power of n minus 1 and b. Now we've got a to the power of n minus 2, b squared. So our powers of a are decreasing each time, our powers of b are increasing each time. And in summation notation, you could write it like this. All right, so that's an introduction to binomial expansions and Pascal's triangle.